Hi everyone, my name is Yihang Fang. I'm a first year math student in Geoscience Department of University of Wisconsin. And today I'm going to talk about modern dolomite from Manito Lake, Great Plain, and its implications. So first of all, why do I want to study dolomite? Because dolomite is a major component of the carbonate reservoir, and also because dolomite is kind of weird. You find tons of them in the ancient rock record, but it's kind of rare in the modern setting now. And there's a famous dolomite problem because it's hard to synthesize in labs under surface condition. And one group tried to synthesize dolomite under using supersaturated solution within 32 years, and they failed. And some people think that dolomite formation is largely related to microbial activity. So we think that might be true. And first of all, I want to show you guys what is dolomite. So you have calcite here, so it's CaCO3, very simple. And then if you replace half the calcium with magnesium and then they become ordered, you got this ordered dolomite. And then so you got one layer of calcium, that's the blue one, and you got one layer of the magnesium, that's the yellow one. And if you just get a dolomite, sometimes they're disordered. And if they're like 50% magnesium in the crystal lattice, then you have they would be randomly distributed. So like this atom have 50% chance to be calcium or 50% chance to be magnesium. So how did it form? Our research group tried to synthesize dolomite in the lab. So because we think it's related to microbial activity, first of all, they tried to use polysaccharide, so sugar, try to synthesize dolomite in the lab. And because the hard part for dolomite to form is because the magnesium will bond with the water and it's so hard to get into the crystal lattice. And they think polysaccharide can help to weaken the bonds between water and magnesium. And then they successfully synthesized dolomite, disordered dolomite. You can see in the XRD data here, that's really weak. And so polysaccharide works. What else? What's the next step then? So they use EPS. So polysaccharide is a major component of the EPS, and they also successfully synthesize dolomite using EPS adding to the solution in a reasonably short time. But how does it exactly work? So one of our PhD students tried to use molecular dynamics to simulate the trimannose. That's the only one we work on right now, to try to run the modeling on how much the sugar helped to weaken the bond between water and magnesium. And it turns out that it lowered the bonding energy for like about 0.7 to 0.8 kilocal per mole. That's pretty significant. So it turns out that like sugar is really helping the magnesium to get into the crystal lattice to form dolomite. So now we move to my study. So I was working on natural samples. So where can you find modern dolomite now? Dolomite mostly found in stromatolite right now, and they're mostly in tropic setting. Like the talk we heard this morning, they're from like Bahamas, those area marine setting, really warm temperature. This one is the Manito Lake. It's in Saskatchewan, Canada. It's really in a really cold setting. It's even colder than Madison. And the water level dropped significantly from 1911 to now. So you can see the light blue is the original size of the lake, and it dropped to only about this much now. And because the water is, they evaporate a lot of water, the pH increased from 9.3 to close to 10 now. And also the magnesium content in the lake also increased. So this is what the field site looks like. Surprisingly, we found most of the carbonates are in the form of coated boulder rather than the stromatolite you would expect to see. And most of them are found in like really mafic rocks, and even in the same location, some felsic rock doesn't have any coated boulder, the carbonate growing on top of them. And only on the east side of the lake, we found this pinnacle stromatolite growing. And then if you cut it open, the middle is really black and it's loose and it smells. That probably indicates it has tons of organic material inside of it. And then this is the hand sample. You can see the outside is like what you expect to see in a stromatolite. It's porous, and the rock is very young. From a previous study, they show that it's late Holocene, so maybe less than 500 years old. And so this is the optical images. You can see more clearly now there's a really bright layer and then there's a dark layer. And then we think the dark layers are enriched in the organic material. But how are we going to test that? What's if there is dolomite inside of it? So we use Xray diffraction, XRD. So you have the X-ray source here and the heat sample, and then it's scattered based on Bragg's law in different angle. And then we collect that in the detector for the 2D diffraction pattern, and we use software to convert it back to 1D. So it's easier to analyze. So because this machine can do in situ XRD, so we can actually pick individual points from the rock and then examine the minerals inside of it. So you can see 1, 2, and 5 is like this, and it has tons of aragonite, calcite, and dolomite peak in it. But in the dark area, the 3 and 4, all you can see was just dolomite. You can't find aragonite and calcite in it. Probably some high magnesium calcite, but mostly dolomite. And take a closer look at the dolomite here. This is the dolomite we got from the lake, and this is a standard dolomite X-ray diffraction pattern. And you can see that it's missing a peak here. That's the 015 peak. That's the peak indicating the ordinance of the dolomite. So that tells us our dolomite is really young and is really disordered. But XRD cannot tell how much disordered that dolomite actually is. So we need later analysis for that. And then this is the D104 and the magnesium percentage. So we think that you can use the composition to tell the displacing of the dolomite. But this is the complete ordered dolomite. This is the complete disordered dolomite. Our sample falls into this little red circle around here. So not just the composition are controlling the size of the crystal lattice. It's also the ordinance is also controlling that. So we are thinking about running more experiment to find out where exactly this line will fall on. And then we move to conclusion implications. So it turns out dolomite, because only the really organic rich part of the rock, the stromatolite, we found dolomite concentrated in them. So we think dolomite's distribution are controlled by the organic material distribution. And then also dolomite might be able to use the indicator for microorganism, so that if you ever find a dolomite on Mars, for example, that might be probably from a fair chance to say that it's biogenic, and then it might indicate there's microorganism once living on Mars. And then for the next step, we're thinking about using gas chromatology mass spectrometer GCMS for organic content, so we get a better quantitative relation between the dolomite percentage and the organic materials. And then also using more XRD to get more data points for the dolomites. And then also using scanning electron microscope, SEM, to get the detailed morphology of the rocks for the minerals. And then using EPMA, the electron probe microanalysis, to get the exact composition, because XRD cannot provide you with a really good, reliable information on that. Also, because the 015 peak is really low, we cannot tell you're just using XRD and the refinement. So we need to use transmission electron microscope to get the exactly what's the ordinance of the dolomite, so we can have more correlation between them. And also because TN has EDS attached to it, so we can use EDS to get a much better accurate composition information for that. And I think that's all.
Yeah, I have kind of a weird one. Good talk, by the way. That was awesome. Some years ago, in one of my cultures of sulfur-reducing microorganisms, I saw these really weird structures that I've never gone down the path of trying to figure out what they really are. But I know that they're magnesium and there's carbonate and there's calcium in these structures, and they look like dumbbells, little microbial dumbbells. And I've seen in the literature that it's been claimed some years ago that when you see these things, that they're actually dolomite being formed by microorganisms in the lab. But I have too small amount of material to really figure out with XRD that it's dolomite. So what would you suggest you could do for something like that? And do you think that even could be dolomite? Do you think that there's kind of papers where they suggest that microbes make these little dumbbell structures and unique forms that would be dolomite?
Yeah, I'm not sure about the dumbbell structure, but I think their literature suggesting like sulfide reducing bacteria can promote the growth of dolomite. If you have really small amount of dolomite, not enough for XRD, probably you can use TEM to determine that.
Okay. Awesome. Very cool.
Go ahead, you're right
Okay.
there.
I was just a little confused about how, with XRD, you can only really look at crystalline minerals. So I was confused how you were saying it was disordered, but based on the absence of a peak. But like, why would it give you such a nice XRD pattern to begin with if it was that disordered?
Oh, because the space group for calcite and dolomite are different. So calcite was R bar 3C, and then dolomite was R bar 3. So they're like slightly different because if you get a disordered dolomite, then it would be more closer to the calcite, and they were missing one peak. If you only get that peak, if it's ordered dolomite. So, because once you have ordered dolomite, you have one layer. Sorry.
Yeah, if you could go back to that disordered slide, that'd be awesome, because I guess I just wasn't really understanding what you meant by disordered in this context then.
So, if you get ordered dolomite, you would actually get one layer of calcium and one layer of magnesium.
Okay.
When you got disordered, they would distribute it randomly,
okay,
depending on the orderness of the crystal. So if you have this, you're actually adding more information to it. So
thank you.
Yeah, just a quick comment. Like a student just asked a question. Point is we can or never can run XRD, okay, because we can do micro X-ray diffraction, no problem. But I just let you know, okay, most published papers are called a microbial dolomite are not a dolomite. So most of them are phosphated because they put a phosphate there. Phosphate and magnesium, calcium, they love each other very much, so they form phosphate precipitates. So, and even some papers, but even people purposely distorted the data, okay, fabricated data to claim dolomite. And a student took my course, okay, they have a project to read the papers and find out what's wrong with their papers. So, because dolomite is so important, okay, it's a challenging problem. So, and also very recent, last month, there was a paper in the Journal of Sedimentary Research, paper by Professor J. and Greg et al. From Oklahoma State University. So they just tabulate all those papers. Okay, they are paper theory, they are not dolomite, right? But in some of my students' paper, they claim that not just a dolomite, what are the real stuff in there? So dumbbell doesn't mean like a dolomite, okay? It's not just this simple.